Today we're going to do the second problem off of the 9th worksheet in the Physics Academic Excellence Workshop. So basically what's happening in this problem is we've got a sphere and a cylinder that are rolling up a hill. And it says that the cylinder starts with a speed of v sub c. And it wants to know how fast does the sphere have to roll in order to reach the same height up the hill. So basically what we're going to do is we're going to solve for the height that each of these things reaches. And then we're just going to set them equal to each other and solve for the speed necessary to make that equality true. So the only real difference between the sphere and the cylinder when it comes to rolling is their moments of inertia, and specifically the fraction inside of their moments of inertia. So we're just going to assume that the moment of inertia of some object is some fraction b mr squared. And we know both of these satisfy this with different values for b. So we're going to say, all right, let's take the system to be the object. I'm not going to specify which yet, because then I'd have to do 2 calculations instead of 1. So the system is the object rolling up. And if we want to find height, we've done this a few times, and it makes sense to use the work energy theorem. So let's do that. Let's say the work done on this object equals the change in energy of this object. So the work done in going up a distance h, I'll call it. It doesn't matter what I call it, because I'm just going to set them equal to each other later. But that is, of course, minus mgh, minus because it's pulling in the opposite direction as the motion. And we know that that equals the change in kinetic translational energy since it's slowing down, and the change in kinetic rotational energy since it's slowing down and spinning. So I know I'm going to get 1/2 mv final squared, which I know is 0 because it stops, minus 1/2 mv initial squared, and then plus the kinetic rotational energy, 1/2 I omega final squared, which similarly goes to 0, minus 1/2 I omega initial squared. So now at this point I'm going to do a trick that we often do and say, all right, well this part right here equals minus 1/2, and I is b mr squared. And I'm also going to apply the rolling condition that tells me omega squared equals v initial squared over r squared. So once I do that, I can cancel out these r's, and this term goes to minus 1/2 b v initial squared. So I also notice really nicely these masses cancel. So I could have given you some masses at the beginning, and it wouldn't have mattered because they're all going to cancel anyway. And so do the radii. So those actually don't matter either, which is pretty neat. So right now, we're at a point where we're going to say minus 1/2 v initial squared minus 1/2 b v initial squared. So, and that equals minus gh. So I'm going to make all these minuses pluses. That's fine. I'll just multiply by -1. And then I'm just going to solve for h. So h is going to equal, if I do some algebra, 1 over 2g times 1 plus v initial squared. Okay, so now I know that this is how high the sphere and the cylinder are going to reach, only in terms of b and their initial speeds. So I'm going to say, all right, h sphere equals h cylinder at this point, because that's the condition I want to be true. So I'm going to say 1 over 2g, and this one's for the cylinder, 1 plus, b in the cylinder's case is 1/2, it's 1/2 mr squared, times v cylinder squared, which was the speed they gave me for the cylinder, equals 1 over 2g times, in this case, 1 plus 2/5 for the sphere, and that's going to be called, I'll call it v sphere squared. And then, at long last, if I solve this with some algebra and try to get vs in terms of vc, then I'll end up with vs equals the square root of 15 over 14 v cylinder.